Hello everyone, today we're going to talk about internal forces. So let's see what we're going to learn today. We are going to use method of friction to determine internal forces in 2D load cases. If you remember in a trusses, if you had a truss like this, there was two methods to analyze this truss, right? The first step was to find reaction. What is the reaction in each support? Okay, the black one is or support reactions. And then there was two methods. One was method of joint, so you just need to analyze one joint and keep going to analyze all the internal force. Another method was method of section and write equilibrium equation to find internal forces. So what we want was internal forces inside these members, right? We want internal forces in the members. So similarly, we want to do it in beams or column. Let's see how we can do this. All right, so our outline for today's lecture is first review what we learned, then application of internal forces, what type of internal forces we have, and then as always, learn how to analyze a beam and determine internal forces like step by step. And as always, we apply all we learn in some examples. All right, so far we just learned about trusses and find reactions and also internal force in the trusses. So today we're going to find internal forces in any structures. You might see some example like this. They are a line truss. If you want to model it as a beam, it's similar to a cantilever beam, okay? That we might have different type of load here, okay? So we want to analyze this column and then find what is the reaction in the ground. So far you learn how to find internal forces in all these trusses members. All right, let's look at the big picture of why we want to find internal forces and how to simplify a model. So here is a picture of different type of load we have. So it's a concrete slab. So this is concrete slab. And we have two type of force. One type is dead load. What is dead load? What is dead load? It's like wall, floor, the load that is always in the structure and they are always there. So we call it dead load because they are always there. But we have some load that we call it live load, like your weight in the building or the furniture. They are here today, but maybe tomorrow you want to change the furniture, so we call it live load. Or person here, they are here today or right now, but maybe in a few minutes they are not there. So we call this type of load live load. So after we analyze in future courses what type of load we have, dead load, live load, sometimes we have other kind of load like point load or distributed load. We want to find the internal force that transfer from all these forces transfer to the slab, right? After that, from a slab, these loaded transfer to the column, and from column they transfer to the ground. So we're going to see what size of column or beam we need to design as an engineer. Let's look at another example and see how these loads transfer to the ground. After we find out what type of load we have, we can think of how the load is going to transfer. So we might have some concentrated load, or sometimes we call it point load, or linear load. Like in your truss, the fence is kind of in a linear load, or sometimes it's distributed load. You're already familiar with what is distributed load. After that, all these loads transfer to the slab, and from a slab they transfer to the column, and from column they transfer to the ground. All right, so as an engineer, we want to design this slab, this beam, this column, and design the foundation or footing, and see what type of soil we need for this structure to carry all these loads. All right, what happens if we don't design all these members with the correct uh, size of cross section, or if we don't estimate this load correctly? Let's see what type of failure will happen to our structures. So here, if we have a loading that causes buckling, you can see in this concrete column what will happen. So it fails from the point that we don't have enough cross section, or maybe enough rebars, different rebars here, or sometimes we have a lot of compression, and you can see what will happen for this column that is connected to a bridge. Or sometimes it's type of shear, it works like this, and it's just breakdown from somewhere like this. Okay, so this is three different scenario that we have some failure. So it's very important we find out what is this force that causes buckling, what is this force that causes compression, or what is this force that causes shear. All right, let's just a concept quiz. In multi-force member, the member is generally subjected to an internal. So from your textbook, if you've done your reading assignment, you can tell which one is correct. So it's normal force, shear force, bending moment, or all of the above. Yes, it's all of the above. So we have all these different forces. So in this picture, you can see this one is normal force. This one is shear force. And the blue one is a bending moment. All right, so the next question in mechanics, the force component V acting tangent to or along the force of the section called, yes, it's called shear force. So shear is always a tangent acting like tangential to the surface. So if you have anything like this beam, the shear force is always like this. It's just at the surface. All right. So let's see what's the application of this internal force. So beams are structural members designed to support load applied perpendicularly to their axis. So when we have a bridge like this, we have a lot of forces applied on this bridge, and we want some column to transfer this load to the ground. So to be able to design, this column or beam, we usually need to know what is the internal force. So why are the beam is like that, and internal forces are important in making such a design decision. Again, because it's very important to find out what is the good cross section that can carry all this load, either it's normal force or it's shear force or it's bending moment. So the objective of today's lecture is to find all these three internal forces and bending moment. So we're looking for this at any given point in the structure. Another application you can see for this one, if you look at the bottom, you can see the bottom part of this column are larger than the top part, okay? Why is like that? Because you know this is all distributed load, that if you want to find the resultant force, you know how to find the resultant force, and then it creates a moment. That's why it's very important to know what is a good reactions that can support FR and also shear stress and this bending moment. All right. Another example is the shop crane is used to move heavy machine tools around the shop. So you can see in the circle, the red circle, you can see this part are stronger than the rest of that. So this is another things that we know. We have some forces here that create some moment about this point, and that's why we need a stronger part in this side. Okay, let's see what is the internal force and how we can find it. So in this beam, as always, the first step, if we want to find the internal force at point B, is to find reaction, right? We know the reaction at hinge is two reaction, dx, dy, and for roller, it's only one, right? We want to know what is the internal force at point B. So the first step is to find reaction, because we don't have any force in the x direction. So the x is 0. That's why you don't see it in this picture. And then what is the next step? The next step is to choose a good cut. But the good things about beams is we don't have to think about where is a good cut. Usually the point that we want to find internal forces are a good cut. And then after we cut, we call these internal forces acting at B. Or so far we know how to find internal forces and step by step. Just something about the direction, because maybe you are curious, what is this direction? Is it something we can assume, or is it something that we need to apply some convention? So basically we assume all the time normal force is going toward outside, the shear force going down, and the moment is counterclockwise. So the moment is counterclockwise, and the sign is like this. How we can find out what is the direction in any given point? So this is the convention that we have in the red box. So for the left side, if you want to analyze the left side of the beam, all the time the normal force is going toward outside, the shear force is going down, and the moment is counterclockwise. How about the other side? It's just the opposite. So if this one is clockwise, this one is counterclockwise, this one is clockwise. If the shear is going down for this part, going up for this one. And the normal force is always going outside. But the most important things in design is shear and moment. This is more important than finding normal force. So usually we just focus on finding shear and moment diagram. That is something we need to learn later on. All right. Right, let's just summarize what we learn about step by step. So first of all, we need to have imaginary chord, and it's very easy to find because it's a point that we want to find internal forces. So this is the first step. What's the next step is to find support reaction. Maybe it's better to find the support reaction first and then use the cut, but sometimes like the trusses, maybe we just need to analyze half of the beam so we don't have to find all the support reaction. So the next step is always finding the support reaction. As always, after we find the support reaction, we draw free body diagram for a piece of structure that you want to analyze and show internal forces and bending moment with the correct direction. Okay, and the last thing is apply equilibrium equation to find out what is this normal force or shear force and bending moment. So we're going to solve an example and see how we can find these internal forces. All right, so this is the problem. The loading on the beam is given. The internal force at point C is something we need to find. Follow the procedure. So to do this, first plan to taking the imaginary chord at C. So it's very obvious we want to know what is the internal force at C. What is the next step? Think about you want to work with the right section from the chord at C to point B or work with the other side. So what's the next step? Find the chord and then find the reaction. So we have two reaction at hinge. It's BY and BX. And at roller, we only have one reaction. All right. So what is the next step? Just draw free body diagram for the part that we want to find internal forces. Okay, so I decide to draw free body diagram first and then find a reaction. So the first step, find a reaction. So go ahead and stop the video and find all the reaction at Bx, By, and Ay. For Bx, I can tell it's 0 because if I write sum of Fx equals 0, there is no load in the x direction, so automatically Bx is 0, right? So you can write sum of Fy and sum of the moment to find out what is Ay and what is By. All right, let's see what you get. So Bx is 0. If you get the moment about A, By multiply the distance, which is 9 feet, and it makes clockwise moment. That's why if we make clockwise moment, it's negative, then it's 18 kips. multiply the distance from A, which is 3, and make this one is clockwise and this one is counterclockwise, so it's positive. How we get these 18 kips? It's just 3 kips per feet multiply 6. So it's, you already know how to find this kips over feet multiply 6 feet. You can cancel out feet and it's 18 kips. All right, so I found by. The next step is to find ay. Just I need to write sum of f, sum of y. All right, now I'm going to cut from point C. So I'm going to cut from point C and draw free body diagram of the cut. It's not in a scale, I just made it bigger so you can see how it works. So I only have by, which is 6 kips, and in this part, because I work with the left side, with the right side, this is my convention about direction. So I'm going to find what is VC, what is MC, and NC. Just I need to apply all these 3 equilibrium equations. It's very simple beam that it can be solved very easily. All right, so let's just review the step first. Find reactions. Second step, a good cut. Third step is apply equation of equilibrium. That's all to find internal forces. Internal forces is the most important topic in statics. All right, let's solve another example and see how we can find internal forces. So in this problem, the load is given, the internal force at point C is a question. So we want to know what is the internal force at point C. So from previous lecture, you know, if this force is 400 Newton, it means the force here and the force here are the same. So let's see what is the problem solving strategies is. First, find the reaction. It's By, Ay, Ax. Is it Ax is 0? Not today, because not on this example, because we have some load in the x direction. That's why Ax might not be 0. So stop the video and find the reactions. All right, let's see how we can find the reaction. So in this step is just find the reaction. So Ax is negative 400 because if you write sum of fx equals 0, we have only this one in the x direction. We can get the moment about B and find Ay. Okay, so if you get the moment about B, Ay multiply the distance, which is 5 meters, and it makes clockwise moment, so it's negative, and this 400 multiply the distance from B. Remember, you need to consider distance, perpendicular distance. So the perpendicular distance for this one is 1.2 meter, because I have 1 meter here, 0.2 meter here, so the total distance is 1.2 meter. All right, so this is the distance, and it makes clockwise moment So this is the moment that it creates. That's why it's negative. So this is how we can find their reaction, support reaction. Just before I move on, there are some examples maybe in your homework that it has some forces like this. For example, this is a simply support beam, okay? Then you might have a force like this, 5 kilonewton here, 5 kilonewton here, and the distance is, for example, 3 meter here and 3 meter here. You can replace this system of forces with only one moment. So you can put the moment of 5 kilonewton multiply 6 meter, which is 30 kilonewton meter. So either you can use these forces here like this and this distance, or you just replace it with one moment. Or for example, for this particular example, you can do this. Okay, this is a roller and this is hinge. So if you have 400 and this distance is 1.2, you can replace it with this system. Just put the moment and it's clockwise, and the moment is 400 multiply 1.2. So it's the same system if you see something like this in your homework. All right. So the first step was to find the reaction. What is the next step? So this is the first step. The next step is to cut the beam from the point we want to find the reaction. So this point is point C. So we decide to analyze the right side of the structure. It doesn't matter if you analyze the right side of the structure or left side of the structure, you get the same answer. Just make sure you are mindful about what is the direction, correct direction for all these internal forces. All right, now we have like a simple beam with some loads that are unknown. How many unknowns we have? 3. How many equations we have? 3 equilibrium equation. So you can stop the video and write sum of fx, sum of fy, and sum of the moment equals 0 and find out all these forces that we don't know. Okay, so we want to find these forces. So write sum of fx equals 0, sum of fy equals 0, and sum of the moment equals 0. What is a good point to get the moment? Yes, because a lot of unknown passing through point C, the best point is at point C. All right, let's see the answer. Now, if you write sum of fx equals 0, the only forces in the x direction is 400, which is negative, and nc. Okay, so you can solve for nc. Sum of fy equals 0, the only fy forces is 96 Newton and shear stress. So you can solve for vc. For the moment, usually we get the moment about where we cut. Okay, so sum of the moment about c equals 0 is 96 multiplied the distance, which is 1.5. So 96 multiplied the distance. mc is a concentrated moment, so it's concentrated moment. So we just added the direction is counterclockwise, so it's positive. All right, now from here you can solve for MC and find out what is MC. All right, let's solve another example and see how we can find internal forces there. All right, so this is the problem. Again, the loads are given. Find the internal force at point C. So we are going to find internal force at point C. What is the problem solving strategies? So we need to think about what support we have. So for example, at A is a hinge. How many reaction we have? To AY and AX. We have a cable here. So whatever the force is here, it's the same here. So let's call it T. We don't know what is T. And also we have some distributed load here. How to find the resultant force for this one? You can find the resultant force instead of using this force, which is 150 pound per feet, multiply the length, which is 12 feet, right? And the resultant is 1800 pound, right? So we found out all the support reactions, cable force, and also external forces. Now we are going to find internal forces at C. Let's just do the step by step. So the first step, find the reactions. There are free body diagram, then cut from point C and then find out what is the internal forces. And maybe you can decide either you analyze the right side or left side. So this is the left side of the structure and this part is the right side. Which part do you think it's easier to analyze? For sure, the left side is easier because it's involved only with AX and AY. So stop the video and solve this problem by your own. Okay? Now let's see how we can solve this problem. Okay, so first I want to find the reaction. So the first step is determine the reactions. So to find out the reaction, I just draw free body diagram of the structure. Make sure, similar to truss, when you want to find the reactions, you need to consider the whole structure and then you do the cut, because sometimes students do the cut and then find the reaction, or they see it's a lot of unknown. So we have 3 unknown here and 3 equation of equilibrium. Go ahead and find out what is these forces. All right, let's see how you solve the problem. First, you need to find out a good point to get the moment. A is a good point to get the moment because 2 forces going through A, so I get the moment about A. So T multiply the perpendicular distance from A. What is the perpendicular distance? Is this distance, which is 2.5 feet, right? What is the direction that makes moment? It's this way. It's counterclockwise, so it's positive. How about 1800? 1800 makes clockwise moment, so it's negative. What's the distance? Is 6 feet. So I can solve for T from this equation. The same way we can find out what is the AX and AY from sum of FX and sum of FY equals 0. So in the X direction, it's only AX and this T that we already know what is this T. So I can find AX for AY, this is AY, and this is 1800. So AY is equals to 1800. All right, so I'm done with the first step and second step, determine the reaction and find a good cut. Now it's time to draw free body diagram with internal force at point C. Okay, so I'm going to find out what is the internal force. So here is the free body diagram for internal forces. So here is my internal force. I already found out what is the reaction. So the last step is to find all these internal forces. Some of them are easy to find, like NC. If you want to find NC, the only force in the x direction is this one. Okay, so NC should be equals to this one. For VC, it's easy. For VC, it's easy because it should be, if you write sum of Fy equals 0, this one and this one are the only forces in the y direction. And the last one is sum of the moment about a good point. What is a good point? It's C. If you want to find the moment about C, it's a good point because all these unknown passing through this point. So go ahead, write sum of fx equals 0, sum of fy equals 0, and find all these internal forces. All right, let's see the answer. So like I said, for x, it's only this force and nc, so you can solve for nc. For fy, the only forces in the y direction are 1800 and 450 pounds. You can solve for vc. Getting moment about c is 1800, which is this one, multiply the distance. What is the distance? Is 1.5 plus 1.5 is 3. What is the direction of the moment about C? It's this way. So it's clockwise. That's why it's negative. 450 multiply the distance, which is 1.5. What's the direction of the moment? It creates the moment this way, which is counterclockwise, and it's positive. And don't forget about MC. MC is a concentrated moment, and the direction is counterclockwise. So we can solve for moment about C. So we have all the internal forces. For next quiz is you need to find internal forces. It's in the beam. So make sure you study this chapter very well because it's the most important topic in a static that you needed in future course a lot. All right, let's call it a day. Don't forget about taking quiz and look forward for next lecture, which is solving more problem from internal forces. All right.